Hello everyone. In this experiment, we'll look at how to use a DC motor controller using 8085 microprocessor kit and a DC motor controlling interface. What we are basically going to do is that we're going to use the 8085 microprocessor to control the working of a DC motor. Let's start with the objective of the experiment. So the primary objective of the experiment is to understand how something like a microprocessor can control a mechanical device. The microprocessor by itself can generate only digital signals such as 0 or 1. It doesn't actually have cannot actually produce direct mechanical motion because it doesn't have any circuit for that. So by doing this experiment, we can learn how digital signals generated by the processor can be used to generate a DC motor through an interfacing module and a circuitry. Also, in microprocessing systems, interfacing is a crucial concept. A processor is useful only if we can use the processor to communicate with external devices, like for example a DC motor or maybe a stepper motor, etc. If we cannot use the microprocessor to communicate with the external devices, then the microprocessor cannot be used in such applications. By performing this experiment, we can understand what the out instruction means and what are the input-output addressing ports and the port programming required to operate a motor. To an extent, we can also call this as an application of embedded systems. Yes. We can also study the role of the driver circuits, and we can understand how software timing can directly influence physical motion of the motor. So now we'll look at the working principle of a DC motor. A DC motor basically uses the fundamental concept of electromagnetism, which is force on a current carrying conductor. What it tells is that when a conductor which has current flowing through it is placed in a magnetic field, the conductor experiences a force equal to F. There is a formula for that, which is F equals B dot I dot L, as you can see. And the direction of the force experienced by the conductor is given by Fleming's left-hand rule. In Fleming's left-hand rule, you have to use your left hand and point. You have to extend your thumb, first and second fingers in mutually perpendicular directions. If you do so, then you can assume your forefinger to be indicating the magnetic field, your second finger to indicate current, and thumb to give the direction of the force experienced by the conductor. So that's that's Fleming's left-hand rule, and that's basically the working principle of a DC motor. When we interface a DC motor with a microprocessor, as I told you earlier, we can understand how digital signals can control physical movement. So at the basic level, what happens is we have electrical current and we have magnetic field, which then generates force, which then generates a torque and finally creates rotation. We'll be looking at how that is caused. So yeah, this is just as I had said you earlier, F is equal to BIL. So you can see the animation here. This is basically how it happens. DC current flows through the coil, and the magnetic field causes due to the magnetic field, the conductor experiences some current. Conductor experiences a force, and the force causes some torque, which then allows the motor to rotate. Usually a coil is not placed like this. It's placed on a rotating structure called the armature. It is just to amplify the magnetic field produced by the coil so that it can rotate at a faster rate. This is also the basic construction of the DC motor. These are brushes, and this is the DC power source. These are the magnets, and this is the magnetic field direction. So now we'll be looking at how the DC motor is interfaced with 8085. So one thing that we have to note is that the 8085 uh, cannot directly supply current required for the motor to run, because the 8085 has output ports which can maybe supply current in the range of 1 to 2 milliamperes. This is much lesser than the amount required by the DC motor. So for that we use something known as a programmable peripheral interface. This programmable peripheral interface used in here is the 8255 port. The 8255 port has input and output ports, and here we have used the output ports, which then what happens is the 8255 port provides some programmable output ports. The microprocessor writes data to the port using out instruction. We'll be looking at how the out instruction works shortly. The port output logics high or low. Then these logic signals go to the transistors, which then causes the transistors to switch to higher current to the motor, and the motor receives the power and the motor rotates. That is what happens in the entire experiment. So what happens is we have instruction execution happens, and the output port changes, and the driver switches. Then a current is produced in the motor, which then causes the motor to rotate. We'll look at the program logic now. So this is just mnemonics. MVI-A means move immediate, and A is the accumulator. EF is the 8-bit data that has to be loaded into the accumulator. That's what MVI-A means. And out 40H. So what this does is it sends a specific binary pattern to an output port. What out means is we out, for example, if we have out 40H, what it does is there are some contents in the accumulator, and the contents in the accumulator are copied to this port address. That's what this instruction does. And then we call delay. The pattern, for example, this pattern is sent to 40H, and this is the final bit pattern of it. This activates certain transistors, which then allows current to flow through the motor, and this finally results in mechanical rotation. So what happens is we have an instruction, then the port output is created, then the driver switches due to this bit pattern, because the transistors receive this bit pattern, then the current flows, then a magnetic force is experienced, then a mechanical rotation is produced. So now we'll be looking at the video. So now we'll be looking at the video which was captured while the experiments were being performed. First, let me show a video that shows switching of direction of the DC motor rotation. So you can see in this video, first you can see here that G2000 is pressed and then enter is clicked, but the motor actually does not rotate because it still has some moment of inertia, and the motor started rotating after some torque was given. Here you can see at this specific portion it started rotating, and this was the switch used to change the direction. However, you can see in this specific part that the motor actually You can see here the motor is rotating in a specific direction. It still hasn't started rotating. Yeah, it is rotating in a clockwise direction, but now after changing the direction, you can see that it's rotating in an anti-clockwise direction. It's not very clear in this video, but you can get the idea from this. I'll also show the, yeah, you can also check the kit in this, kit commands which were entered. D3 is the speed of the motor. D3 is actually not a very big number. D means 16 and 3, which means 19. So out of 55, we have taken 19, which is not a very high speed for the DC motor. Now let's move on to the next video, which will show the stopping of the DC motor. I've zoomed in too much. Here you can see the motor is rotating, but here the speed is given to be 88 first, and then it's changed to 00, but we still haven't executed the instruction by pressing G2000. And you can see here, immediately as G2000 shift 4 is pressed, the motor stops rotating. It is very clear. You can check here. Yeah, the motor stops immediately as G2000 is entered. So now let's move on to the next video. You can check in this video. The motor actually does not rotate for every speed. There was a minimum speed at which the motor rotates. Because ideally, although the motor should rotate for even the lowest speed possible, so most of the times it doesn't, because there is because of some frictional effects, or because of old equipments or other reasons like that. Now I'll show you how speed can be changed in this. So this is a very high speed. You can see that a pattern is produced here, and this pattern will be different for different speeds. So this is very fast now. We still haven't changed the speed. So M2001 FF is the highest speed that can be achieved. So now G2000 is pressed, and M2001 is changed to AA, which is a lower speed, but we still haven't executed it. So immediately as we press shift 4, you can see that the pattern has changed a little bit. Can you see it? So this is a different pattern. It's almost like a circle, and for AA it's almost like a square. The pattern has definitely changed. This will be even more clear while using a slow motion video, which I will also do after this. So now I changed it to 6.6, which changes the pattern even further. So you can see, you can almost not see the pattern now. Just like how while a fan rotates, you'll not be able to see it. It was the same case for this when the speed was high, and now we have changed the speed to 6.1, and G2000, this would execute it. You can see that the pattern has reduced even more. In fact, if we reduce the speed even lower than this, the motor might actually stop for reasons I had already explained. So it's 5.8 now. 5.8 is even lower. It still hasn't been executed. Yeah, the motor has stopped. This is not because 5.8 is the lowest speed it could run. This is because of some frictional effects. As you can see, even if we give a push, the motor is not rotating. It rotates a little, but not completely. It's very obvious from here. despite our best efforts to run the motor at the low speed of 5.8, it was not possible. It's 5D now, and we are changing into 5F, a little higher. The motor still doesn't run, even after giving a push. Let's move on to the next video now. So as we changed the speed to a higher one, it started rotating very fast. The next video is more interesting. Let's look at that. You can see here, it's M2001. Speed is 00. And it's changed to FF now. And the motor starts rotating very fast after we execute it. Yeah, as you can see, the motor is rotating very fast here. This is the J5 pin that I explained earlier. This is a 50 pin FRC cable. So now the speed is changed to 8.1. It has reduced a little bit, but it's not very clear in this video. And now we'll be changing the direction of rotation. You can see how the motor is rotating. The direction was actually changed at this point, but then the motor, for reasons I explained earlier, it did not run. So we tried to make the motor run manually by pushing it, giving it a small push. And after giving it a small push, it indeed worked. You can see that here. Yes, this is a different direction from earlier, as you can see that clearly. I would explain this would be explained even better in the next video actually. So yes, this is a slow motion video. You can clearly see the motor rotating. It's in speed FF, as you can see here. The motor is rotating in a direction, and this is the point at which the direction of rotation was changed. As you can see, the code doesn't have any difference because we don't have to make changes to the code to change the direction. There is a key in the ET-DCM module which can be manually used to change the direction of rotation. It just reverses the polarity in the coil of the DC motor, which is bound to the armature as we saw earlier. So that's it. Thank you.